All right, so in this is we're going to look at sound in particular and look at how sound works in the air. And what sound really is it's a longitudinal wave. Normally we perceive it as a longitudinal wave created in the air. The pitch of sound that we hear is related to its frequency. Our brains kind of convert frequency into pitch. For the average human, that pitch is somewhere between 20 and 20,000 hertz. That range is what you can hear. There are some ways you can damage your hearing. Usually if you've damaged your hearing, you lose your upper frequency hearing, your high frequency hearing first. Some ways your hearing can be damaged. You can have hearing damaged by multiple ear infections as a child. You can have hearing damaged by listening to loud music frequently. You can have hearing damaged by listening to loud or being exposed to loud sounds on a regular basis. So there's lots of different ways your hearing can be damaged. Also, generally as you age, that higher end starts to decrease. Other animals can hear much higher pitches. Dogs can generally hear up to about 50,000 hertz. That's how a dog whistle works, that you can't hear it, but a dog can hear it. It's above 20,000 hertz and below 50,000 hertz. Bats can hear sounds up to 120,000 hertz. Those high frequency sounds that bats emit are really the way that they see the world. Since they fly around in the dark, they have decent eyes. They actually have pretty good eyes, but they have better ears. They actually see by listening to what's going on around them. So the speed of sound in air is pretty close to about 330 meters per second. Sound can also be used in sonar to determine the distances from objects to other objects. So here's kind of a quick diagram of how sound works. If we looked at this slinky, sound is a longitudinal wave, so the wavelength is from one area of compression to the next area of compression. And we see areas where the particles are compressed together and areas where they're spread out, areas of compression and expansion. We also see this if we looked at the sound waves traveling away from this speaker toward this person's ear. How your body actually perceives sound is with an area of compression, your eardrum goes this way. With an area of expansion, your eardrum goes that way. And so it's this vibration of your eardrum that actually allows your brain to perceive that sound. So the speed of sound, as you probably guessed, sound travels at different speeds in different materials, and there's a lot of different factors that play a role in how fast sound will travel through material. Things like density, temperature, flexibility of the material, what types of particles make up the material, how are those particles bonded to one another, all sorts of different factors. This can get quite complex, as you might imagine, and you can actually go look in the book online in chapter 16.6 for some examples of how complex this actually gets. What we're mainly interested in is how fast does sound travel through air, and in normal air, under normal pressure conditions, the speed of sound is proportional to the temperature in degrees Celsius. Higher temperatures have higher speeds of sound. And here's the equation that you can use to calculate the speed of sound based upon temperature T in degrees Celsius. 331.5 plus 0.607 T. So let's do a quick problem here. And what we want to do is figure out the speed of sound on both the hottest day ever recorded in Minnesota and the coldest day ever recorded in Minnesota. And so Minnesota happens to be one of the more extreme climates in the United States. You could maybe go to North Dakota and find a state with a more extreme climate, but in terms of places in the United States, Minnesota is up there toward the top of the list of most extreme climates. We have also one of the more extreme climates in the world here. You pretty much have to go to places like Siberia or Mongolia or places like that to find more extreme climates. So the hottest temperature ever recorded in Minnesota is 114 degrees Fahrenheit or 46 degrees Celsius. That was on July 6th, 1936 in Moorhead. I should put another asterisk here. It's worth pointing out that 2 days later in a town of Beardsley, which is south of Moorhead, the same temperature was recorded, 114 degrees Fahrenheit. The lowest temperature ever recorded in Minnesota was negative 51 degrees Celsius, which is negative 60 degrees Fahrenheit, on February 2nd, 1996 in Tower, Minnesota. It's also worth pointing out that there is an unofficial temperature of negative 63 degrees Fahrenheit recorded a few miles away from Tower. This is the official National Weather Service temperature for that day. I do have for reference because I was alive and lived in Minnesota on February 2nd of 1996. My hometown of Litchfield, Minnesota was a comparatively balmy negative 44 degrees Fahrenheit that day, or negative 42 degrees Celsius that morning. This would also be the day, if you are somebody of my age that lives in Minnesota, that you would remember that the governor of the state of Minnesota decided that no kids could go to school in the state of Minnesota. One of like 3 instances that has ever happened. So let's calculate the speed of sound at these various temperatures, and it's actually a pretty easy calculation. Plug in my temperature, and what we find is that the speed of sound has varied from 359.4 meters per second on the hottest day to 300.5 meters per second on the coldest day. And so this difference of 50 meters per second, or 60 meters per second almost, would make a difference in lots of different things if you were trying to use the speed of sound to calculate something. So there are other types of waves too that we could look at that we use. One of the other types of waves that our body makes use of on a regular basis is visible light. Visible light is really a transverse wave of electric and magnetic fields. One interesting thing about visible light is it can pass through a vacuum. Sound cannot pass through a vacuum. And the wavelength of light, which is related to the frequency of light, is actually related to the color your eye perceives. So your eye perceives longer waves, lower frequencies, more red, and shorter waves, higher frequencies, purplish and blue. The speed of light in the vacuum is 300 million meters per second. It's worth pointing out in sound it's about the same. The speed of light can also vary depending on the nature of the material. Save that idea for later as well. Now, light is one of a whole encompassing type of wave called electromagnetic radiation. These are all transverse waves of electric and magnetic fields that can pass through a vacuum. And the type of radiation usually depends upon its frequency. I say usually because there are some overlaps here. Radio waves generally have frequencies of less than 10 to the 9th hertz. Microwaves in the 10 to the 9th to 10 to the 12th hertz. Infrared in the 10 to the 12th, 10 to the 14 hertz range. Visible light 10 to the 14th hertz. UV light 10 to the 14th, 10 to the 17th, and then gamma rays, X-rays greater than 10 to the 17th hertz. Also happens to work out the frequency and energy relate to one another in terms of electromagnetic radiation. So radio waves lowest frequency have the lowest energy. Gamma rays and X-rays in that highest frequency, highest energy. The reason why gamma rays and X-rays are combined here is that their frequencies overlap. What distinguishes a gamma ray versus an X-ray is how the type of radiation is actually formed. Gamma rays are normally formed by transitions of electrons in the electron configuration. X-rays are generally formed by either nuclear transitions within the nucleus of an atom, or formed by accelerating charged particles around curves. That's a fairly technical distinction between these two. What you would need to know is that these are the highest energy, highest frequency types of electromagnetic radiation. So that's kind of a quick overview of sound and got into a little bit of electromagnetic radiation. What we'll look at in the next lesson is how do we measure intensity of sound? What is the way that we use to describe sound intensity?